Are there any questions? I believe you had some.
Yeah, this one, number 2, I just wanna make sure, I drew the picture.
Okay.
Are these supposed to be separated? Or was that
Oh,
typo?
that is bad editing on my part.
Okay, so is this correct then? If I
We're
do
gonna
this?
add a 4th resistor in order to increase the flow of electric current out of the battery. Yes, you just have to put it someplace in parallel with
Yeah,
one of the other resistors.
okay, so I could have done it here or here as well?
Yeah.
Okay,
Loads of places, just so long as there's another pathway.
yeah. Well, that's why I did it in here, cause I thought these were separated. So I thought if I do it in here, it'll connect it. Would that work as well? Cause it's parallel.
Yeah, that would work also.
Okay.
And if it were separated, if that were not just bad editing, then
would
put it across the battery to actually do making circuit
Yeah, within,
would do it too.
number 3, I don't think we did this at all.
Oh, no, okay. That's the whole balloon on head. Well, why don't I go grab that?
Okay.
I'll be right back. Just gonna let the camera roll. Let's do one.
Sounds like it.
That's crazy. So basically, we want the test to look just like this.
And rate of change.
You're like, this one is for the.
In California? Yeah. We're from California. I went to Seven, okay? I've been there once.
What?
It's really
It's all finding the fur. All right, this is an electroscope. And hopefully you can see the two things dangling down with the white background. Perhaps that middle of the class should work a little better. All right, I'm hoping you can see that. What you need to do is just get a charge near it. And so a nice way of doing a charge is PVC pipe and rabbit fur. Doesn't always, when you rub two things together, it doesn't always mean that the electrons are, well, actually, it does mean the electrons will be moving from one object to the other. In this particular case, it's the electrons moving from the rabbit fur onto the PVC pipe. So as I bring this near, hopefully you can notice that the leaves are starting to move apart. So I bring it near it, and they spread, take it away, and they collapse back down. So first off, why? Okay, well, if one repels the other, they have to, Newton's third law is in play there. All right, so the electrons, what happens to the electrons that are repelled from here?
Do they go down?
Okay, I think I saw a finger in the back as well. They go down into those two light bits of foil. I believe that's aluminum foil. Some sort of foil, probably aluminum is cheap. So the electrons go down in there. So why do they spread?
Because they repel each other.
Yeah.
No, because if the electrons are, because they wanna go against each other.
When you say go against each other, do you mean repel?
Yes.
Yes. So I'm driving electrons away from here, down into there. And you could make an argument that protons are attracted, but don't make the argument that the protons are moved up into the ball here. Because the only way the protons will move is to move. But the protons are not getting sucked up towards the ball. The electrons are being repelled down, making those negatively charged. So why do the leaves go back to normal when I take this away?
Because the protons aren't being forced down anymore. The electrons.
Reword that, say it again.
I'm trying to think how to reword it.
You said protons.
Yeah, protons aren't being forced down anymore.
Protons were not being forced down to begin with.
Or electrons.
Yes, that was the key thing. Yes,
Yeah.
the electrons aren't being forced down, the danger is past, they return home. All right, so now what's gonna happen if I touch this to the knob?
They'll stay apart.
You said go stay apart?
The leaves.
When you say stay apart, as long as I'm touching it, or if I remove it?
As long as you touch it.
All right, so touch it, they do go apart. And now, when I take it away, what's gonna happen?
They'll go back together. But it's
Not
still-
completely.
No, then it's still apart.
Why? What's the difference between my touching it and not touching it? Besides, the leaves didn't go back to normal.
I guess more electrons were moved by touching it than not touching it.
Were moved?
Yeah, more electrons moved from the PC pipe into there when you touched it than when it wasn't touching.
Okay. How many electrons were moved from the pipe to that when I did not touch it?
A smaller amount.
Much smaller amount. It probably, unless you hear or see the spark, it's probably close to zero.
It
Ashley?
would stay like that forever if you,
It would make so many electrostatic experiments work so much better if that were the case.
but it'll just slowly come back together.
This time of year, yeah, they'll slowly come back together. What's happening to the electrons? It's not like the electrons lose their power.
They're just moving.
Pardon?
They're moving.
Where?
Probably back up to the knob and into the air.
Into the air is the key thing there. Except air in itself is an insulator. What part of the air is it getting attracted towards? What's pulling it off?
Proton.
Let's be more specific. My first wording was poor. What in the air,
Oxygen. Or carbon dioxide.
not the carbon dioxide. I think carbon dioxide, aren't the oxygens sort of opposite each other?
Yeah.
Wrong tiny thing that's in the air.
Monoxide.
What'd you say?
Carbon monoxide?
No.
Okay.
I guess potentially, but I don't think there's enough carbon monoxide to make a difference. I will tell you, here's a hint. When we do this in summertime, they would have collapsed by now.
Is it warm air versus cold air? Because warm air moves faster than.
No, that's not the reason. There is a difference between warm air and cold air, but the warm air has something else in it that the cold air does not, or warm air has more of it than cold air.
Water vapor? Water vapor?
That's it, that's the key. And the reason why water vapor causes it is that water is H2O, and you have an oxygen molecule here, and then the hydrogens kind of hang off at an angle like this. Hydrogens have one electron, they want two. So oxygen is sort of missing two of the electrons from being its completeness, and so they share. So since the hydrogen is sharing its own electron over here and its oxygen is sharing one, it's leaving this side sort of exposed. So this side is positively charged. Over here, we've got some electrons hanging out over here. This side is negatively charged, and so a water molecule is considered to be polarized. There's a positive and negative side to it. Carbon dioxide, I was thinking, it's not polarized, it's evenly distributed. And I could be wrong on that one, but that carbon dioxide typically is not the deciding factor. And so now I have an electron here. I have excess electrons, they hate each other, they're trying to get away from each other. There's nowhere to go except this water molecule comes along. It's got a positive side, the electron goes, ooh, positive side. And we'll try to make the jump. If there's enough water vapor in the air, it'll jump quickly and those leaves will start to collapse. So how do I collapse them? Now that they're charged.
Spray water on
That would do it. What's a simpler way? Although we do have water right there.
Touch it.
Yeah. What's happening is that the electrons want to get away from each other, and so by my touching it, I'm a much bigger surface than the ball is, and then the leaves. So I'm sort of considered to be a sink in a way. I'm ground. I count as ground.
Could you touch like a cardboard box against it and would do the same thing, or does it have to be you?
Let's see, we do have a cardboard box here. Let's find out. I don't think the cardboard box is going to work as well.
So when you touch it, the electrons are moving out of there
Into me.
into you.
If it touches a big enough surface, like a human body or the ground itself, the earth itself, a ground basically is going to either take the electrons off if they're excess electrons or give electrons if it needs it. Because I have so many of them, I can easily just take more than it can handle. You can also touch it to a frame, some piece of metal. So you were asking if the cardboard box would work?
More like you just touched it. Like you still do the same thing and it's like wide apart. But if you touch the cardboard box to it, like what you did.
Ah, okay. Well, I'm curious about this part now, so we'll get to your question in just a moment. So what I'm doing is I rub these two things together, basically, in essence, scraping electrons off of it. If any of you have dragged your shoes across shag carpeting especially, for those still living in the 70s, I'm looking forward to shag carpeting coming back as a fashion. I guess they're gonna wait for a generation to die off and then harass you.
I just think it's too many germs in a shack.
All right, so that's not doing anything. The cardboard, certain materials don't have enough of a absence of electrons in order to take any of them, or they're just not good surfaces for picking it up. PVC works really well. However, is that still
So
charged?
would PC be considered a conductor?
No.
Not an insulator.
Oh, no, it is definitely an insulator.
Insulator.
If it were a conductor, and we could test that out also, well, let's actually answer Ashland's question, and then we can talk about what happens if I did it with a conductor.
not as well as you think.
It's not as big and, yeah. So if I take a conductor, there's a bar not screwed in. And so let's scrape some electrons against it. Oh, probably should ground that thing. Now this should not work. I mean, in other words, the leaves should not go apart. But then the question is going to be why? Why is this not going to work? Not for the same reason as the cardboard, I believe. Why does a conductor not work well when doing that demonstration?
Because it's not taking on more electrons?
Not necessarily. If it took on more electrons, what would happen?
I would think it would spread apart.
Why is this a conductor?
It's metal.
Okay, what is a conductor?
It's, well, I thought electricity is supposed to move more quick, well, heat is supposed to be low.
We're talking about electric conductivity.
I would think it would move more quickly through conductors, whereas with insulators, it kind of blocks the movement of the electricity.
Okay, so if I have this and I put excess electrons on it, where did those electrons go?
They wanna go to the earth, don't they?
They do. What's the best substitute for it? It's not touching the earth right now.
You.
Yeah. So any excess electrons get on here, they'll repel each other, and they'll, unlike the insulator where they can't go anywhere, they're sort of stuck. Think of it like a glue trap. This, definitely not a glue trap, and they're just gonna rush into me.
Okay.
And so I should have excess electrons, but because of a large enough surface, any excess electrons get spread out, and potentially I could be charged, but not significantly.
Okay, so it's better for an insulator to touch that.
Oh, absolutely, if you
for
want
it
to,
move. An insulator with excess electrons.
yes,
Okay.
yes. If we take this right here and let's discharge it,
No.
hopefully that's enough. So in theory, I've drained the electrons off of it. And there's still some residual stuff, but not as many as there were before. So just having an insulator is not enough, it does need to be charged. Ashley?
Are you an insulator, or are we insulators or conductors?
Yes.
What?
Nothing is actually a pure insulator, nothing is a pure conductor. Conductors will have, I guess you could make an argument for superconductivity,
No.
but there's gonna be some resistance. And so we're not an ideal conductor, at least. Now, if I took two pieces of metal, stuck it into the outlet, touched it, yes, that electricity, there's high enough voltage, that electricity wouldn't conduct through me. With a bad ticker, the heart would seize up. But at the same time, you need a high enough voltage. I can touch two ends of a 1.5 volt battery and I'm not gonna feel that. So. Does that answer your question?
I think so, cause like, people get struck by lightning all the time.
Yeah, there's a huge potential difference there, and, yeah, it is trying to get to ground. So what happens is the electrical signals get basically sent through your body, and I'll show my ignorance of biology now, essentially, correct me if I'm wrong. When the electrical to get the heart to pump, you send an electrical signal to it and it tightens up. And then I think it's just lack of an impulse which causes it to relax. And so there's, waiting for someone to correct me if I'm wrong on that.
Sounds right.
Is that right? And so if you have a lot of electricity going through you, then suddenly it will tighten up and not release.
And is it better to use an insulator because these are two different conductors?
No, it's once I put the charge on the insulator, the better the insulator, the better the demonstration. Once I put the charge on the insulator, the charge doesn't go anywhere. It doesn't naturally want to, well, it wants to, but it's stuck.
Yeah.
And so it'll keep the excess charge localized. So when I touched it, I moved it back and forth because if I touch it here, then I'm gonna pull these electrons off, but these electrons are still here.
Okay.
So I did this in order to get more electrons into the electroscope. And by the way, a number of years ago, I had the electroscope question on it, and I made a reference to the light leaves. And the two bits of foil hanging down here are the leaves. Light as in don't weigh much. There was, I think, a couple students who mistook it for light as in shining,
Yeah,
not as in not weighing much.
yeah, that's right.
Other questions? Anaya?
Question 12. It's long.
The 12, sorry. The Goldilocks.
And the one at the bottom.
Goldilocks.
And this one or that one?